Okay, so today I want to talk about these sections right here, mostly section 3.1, and we're going to be talking about modeling using differential equations. Okay, so we're just kind of starting out, so we're going to be focusing on first order models, and they are going to be linear models. Okay, and so kind of the main idea in this case where we're dealing with linear and first order, the idea is we want to know about something and we know that its rate of change, its derivative, is proportional to itself in some way. And so we get a differential equation that looks like this: dx dt equals kx. And we've looked how this solve this. This is a linear equation, so we could use an integrating factor to solve this as well. Okay, but we're going to start to apply it to different, more real-world scenarios and see how that plays out. So let's just kind of hop in because each situation is a little different. You kind of think about what's going on in the real world and understand the situation itself. Okay, so one of the first examples is thinking about populations. Okay, so let's just read this example. So the population of a bacteria in a culture grows at a rate proportional to the number of bacteria present at time t. So that's exactly the situation here. The amount of bacteria, the change in that bacteria over time is proportional to that value itself, the number of bacteria itself. Okay, and we're given some data. So it says after 3 hours, we have 400 bacteria. After 10 hours, 2,000 bacteria. And then the question is, what was the initial number of bacteria? So when we mean initial, we mean at 0 hours. Okay, so in order to set up this problem, it's helpful to kind of create some labels for things. So for example, you can we want to think about the number of bacteria. So let's pick a variable for that. And so for example, in this case, I might pick P of T to be the number of bacteria at time T. Okay, so that gives us a variable to work with. And then that first sentence, it says the population of bacteria, so that's P, grows at a rate proportional to the number of bacteria. So that tells us this. It tells us that dp dt equals some proportionality constant, k, we normally use, times p. Okay, so that's our differential equation. We know that from this sentence here. Proportional means, sometimes we write proportional as this. Change in p with respect to time is proportional symbol to p. And that's equivalent to this statement right here, that is equal to some multiple of the population. Okay, so we know this differential equation, and then we know a couple other things. We know that at 3 hours it's 400, so P of 3 equals 400, and P at 10 equals 2,000. And then what was the initial number? The question is, what was the initial number of bacteria? That's basically saying, what is P, asking us, what is P of 0? So that's what we're trying to find out. Okay. So basically, there are a couple things we don't know. We don't know what P is. If we can find a formula for P of T, then we can find P of 0. But we don't know what K is right now. So we're gonna need to think about trying to figure out what K is. Okay, so it's kind of the two things we're trying to understand. And so basically, generally the first step in this type of problem is to solve the differential equation. So let's try and solve that differential equation. That'll tell us a formula for P of T. So dp dt equals k times p. That's separable. So we could write that as 1 over p dp equals k dt, and then integrate both sides. That'll give us the natural log of p equals k times t plus c. And then solving for p, we take the base e of both sides, we get p is equal to e to the kt plus c. Or using our exponential rules, we can rewrite that as bring the constant down as some other constant, e to the kt. Okay, so that's our formula for the population here. We know p of t is c times e to the kt. Okay, we don't know what k and c are. Okay, but we have these two formulas up here. That'll help us solve for c and k. So we just answer this question, p of t is equal to c e to the kt. All right. So once we find c and k, then we can plug in 0 and p of 0. So in fact, p of 0 is going to be whatever this constant out front is. Okay. Because when I plug in 0 for t, that e to the 0 goes to 1. I think it's going to turn out, though, that we need to find k before we can find c. So we'll have to just kind of work through this. So that's basically, we take these two equations and we plug them in. So we get p of 3 is c e to the k times 3. That equals 400. And p of 10 is c e to the k times 10. That equals 2000. All right, so we have two equations, two unknowns. We want to solve for k and c. When we're doing this, so this is a little tricky because there's an exponential. The way we want to solve this is we can actually divide one by the other. So if I divide this second equation by the first one, I get 2000 over 400 is going to equal c e to the k times 10 over c e to the k times 3. So that's helpful because it cancels our c out, and we can just solve for k. So 2000 divided by 400 is, that equals 5. And e to the 10k divided by e to the 3k, that equals e, we subtract the exponents, the 7k. So we have 5 equals e to the 7k. Take the natural log of both sides. That cancels out the e, so we have 7k. Natural log of 5 divided by 7k, so then is natural log of 5 divided by 7. Okay, that gives us our constant k. And now that we know what that is, we can plug that in to one of these equations up here and solve for c. Let's do that on the back here. So we have c e to the k, which is natural log of 5 or 7 times 10 equals 2000. Okay. All right. So trying to simplify this a little bit, we have an e and a natural log. We'd like to kind of cancel those out, but we have this extra constant here. So 10/7 constant out front can actually go, we can bring that into the exponent of the 5. So this is like e to the natural log 5 to the 10/7 power times c equals 2000. And then the e and the natural log cancel, so we're left with c times 5 to the 10 over 7th equals 2000. And then just divide that constant, our c is equal to 2000 divided by 5 to the 10 over 7. Okay, so that'll be some number. You could plug that into your calculator. I won't do that right now. But you can find that out. That's our constant c here. And like I said before, when we plug in 0 to p, we just get this c out, ce k times 0, just c, which is what we just solved right there, 2000 or 5 to the 10 over 7. Okay, so that's our final answer right there. Is that's the initial amount of bacteria at time 0. So not too hard. It's just we're using our knowledge of differential equations, applying it to answer a question about the situation. Okay. It basically involves setting up a differential equation, solving it, and then we just basically an algebra time. So we had to do some algebra to solve for the right constants. So that's our kind of our first example. Here's another example. So all these examples are going to be different situations, kind of just outlining. And so I can explain what the situation is and how you might think about the differential equation that goes with that situation. Okay, so here we have another example. We have a thermometer. It's reading 70 degrees. It's put in an oven, and the oven has a temperature. Okay, we don't know what that temperature is. And then we watch the thermometer, and we see that after half a minute, it's 100 degrees, and after one whole minute, it's 145 degrees. And so we're trying to figure out, the question is, how hot is the oven? So this is an example called Newton's law of heating and cooling. And what does that say? It says that the basic idea of Newton's law of heating and cooling is that the change in temperature with respect to time is proportional to the difference from the outside temperature. So if T sub 0 is the outside temperature or the ambient temperature, and capital T is the temperature of the object we're measuring, the rate of change of the temperature is proportional to how different it is. So, if you put an ice cube into boiling water, it's going to melt really fast because the difference in temperature is really high. But as it gets closer in temperature to one another, then that change in temperature is going to be lower. Okay. So, if you put ice outside where it's cold, that change in temperature is not going to be very high, very large. So that's the idea here. So in this case, so T is the temperature of the thermometer. And if we're going to be being careful in degrees Fahrenheit, T sub 0 is going to be the temperature of the oven. Again, in degrees Fahrenheit. And T will be our time in minutes. And we know that this situation here, this is described by this differential equation. Okay, so that's just something that you would have read in your book, or could looked up kind of this physical law. Okay, but we can see that it kind of is in that same situation. It's linear. T is linear, and it's first order because we only have a first order derivative here. And so we're given a couple of things. We know that T 0 is 70 degrees Fahrenheit. T a half is 100 degrees Fahrenheit, and T of 1 is 145 degrees Fahrenheit. Okay, and the question is how does the oven? We want to figure out like T not 0. Okay, that's what we're trying to figure out. So again, kind of the first step is, along the way, we kind of realize we're probably going to have to figure out what is this K, and then there's going to be also an integration constant as well when we solve. So what is the C? So that's where we have these three unknowns. We have three equations. That kind of makes sense that we can hopefully should be able to figure that out. So first step, solve this differential equation. Again, this is actually separable because there's no small t in there at all. So this becomes 1 over t minus t naught d big T equals k t time. Okay. Integrate both sides. Get this is kt plus our constant. And this is again going to be a natural log, but now natural log of t minus t naught. Solving for t for the temperature, take base e of both sides. Okay, let me just skip right here. We can bring that constant down with e to the kt equals t minus t naught, and then add that across, t e to the kt plus t naught. Okay, so that's our formula for the temperature of the thermometer in oven as time goes on. But again, we don't know. We're trying to find what this T0 is, but we don't know what the K and the C are either. Okay, but we do know these three pieces of information right here. So let's just kind of plug those in and see what we get. So we get T of 0 is 70. That means that 70 degrees equals C plus T naught. T of a half, 100, so we have 100 equals C E the K over 2 plus T naught. And then T of 1, 145 is C E to the K plus T naught. So somehow we want to solve for T0, T naught. It's our goal here. So what might we try and do? This first equation here tells us if we know what C is, then we can find what T0 is. Okay, so we need to try and solve for C. Okay. So how might we solve for C? We probably try and use these other two equations here. So I haven't done this before. Let's just kind of try some different things. So maybe I'll try subtracting this third equation from the second equation. So we have 145 minus 100, it'll be 45. We have CE to the K minus CE to the K over 2. And the T0 minus T0 cancels out. So does that help us at all? Mm-hmm. Can factor out the C. So e to the k minus e to the k over 2 equals 45. We have another formula for C. So I guess what I want to do is I want to divide, like we did in the example 1, in order to cancel out the C's. But this extra T naught here, if I divide, is not going to allow me to divide very easily. So anybody see any ideas about how to solve this right now? Just giving you guys time to work this out on your own if you're listening to the recording. All right.
If you just substitute and do it, I don't know.
Yeah. So I'm getting lost here, but I think let's We could also try subtracting these two equations here, maybe. So let's subtract the second one from the first one. So we get 30 equals c e to the k over 2 minus 1. And the t0 minus the t0 cancels out. This is actually, in fact, this equation here is 45 equals c. I can factor out an e to the k over 2. I get an e to the k over 2 left minus a 1. And here's where I can do my dividing now. Okay, so if I take this equation here divided by this equation here, 45 divided by 30 is going to be 3 halves. The c divided by the c will cancel, and this e to the k over 2 minus 1 will cancel with this e to the k over 2 minus 1. So I just got left with e to the k over 2. Okay, so that's what we want here. That allows us to solve for k. So if I do natural log of both sides, e to the k over 2, this just becomes k over 2. Multiply the 2 across k is going to be 2 natural log 3 halves. All right, so there's k. So that's a good step. Now, just kind of thinking back, if I find k, then I can use either of these equations to solve for c. And then once I find c, then I can use my very first equation to solve for t sub 0. So let's try and do that. So once I know what k is, so k equals 2 natural log of 3 halves. And I also know that 30 equals c times e to the k over 2 minus 1. Right? 30 equals c e to the k over 2 minus 1. Okay. So now that I know what k is, let's plug that in. So we get c, e. The 2 and the 2 are going to cancel, so we just get natural log of 3 halves minus 1 equals 30. The e and the natural log will cancel, so we get 3 halves minus 1 times c. 3 halves minus 1 is just a half. If we multiply that by 2 on both sides, we'll get cancel out that half, so we get 60 equals c. All right, so that tells us that c is 60. And then my last piece of information, I know 70 equals c plus t0. Okay. Can I do this right? So if c is 60, all right, well, that is not good. I made a large mistake somewhere. So this would tell us that t0 is 10. So this is a good learning opportunity. So does that make sense? If the oven temperature is 10 degrees, that does not make sense, right? Because then the temperature of the thermometer may be going down, not up. All right. So it's a good opportunity. Always, when you get to the final answer, you should double check. Does that make sense at all? Clearly, this does not make sense. So let's go back and look a little bit and see maybe if I can find where we made a mistake. So let's actually, I might have made a mistake way at the very beginning. So let's double check this differential equation. What does this tell us? So let's imagine that the oven is 200 degrees and we put in something that's 100 degrees. what should the change in the dt, the change in temperature with respect to time be? It should be positive, right? So if I kind of imagine that, if I have 100 minus 200, that's going to be a negative number. And if k is positive, that means that I'm going to get a negative, I'm going to get a negative rate of change, and that's not right. Okay, so in fact, what I probably should have written it as either as negative k, t minus t naught, or you write this as k, t minus t. So let's imagine that here. So if I have a 200-degree oven and I put something colder than that, this will be positive. If k is positive, then we have a positive rate of change, which is what I want. If something's hotter than it is. Okay, so what does that do to how we wrote the problem? So basically that just flips around this t and t naught here. Here. We'll put the negative here in front of the k. So I put a negative there, negative, negative, negative. That changes things quite a bit. So I'll kind of fill in the negatives here as we go. Negative. So again, let's see here. When I factor out this e to the k over 2, that'll look something like that. So we would add those two things together. That would get us e to the negative k. All right. Negative, negative, negative. So then this is negative, and that becomes a negative here. All right. And so our k becomes a negative 2. We had a apply that across. So k becomes a negative 2 natural log 3 halves. So basically just flip the sign everywhere. K is negative. So the confusing thing here is the two negatives will end up canceling out.
Can you show the bottom of the page real quick?
Yeah, sorry. So I think I made a sign error through here. So let's just kind of double check that through. Negative k, negative k, negative k.
The only thing I see is at the very bottom, you have negative k is equal to negative 2 natural
That's
log
okay.
3 halves.
Yeah, so let's double check
positive
that
k.
here. Negative k. So I think, yeah, positive k, negative 2.
So it should wind up coming out to whatever on the back here being 2/3, right? Because it'll be a negative natural log of this thing. That negative by log rules will be, well, -1 will be brought up into the exponent.
Right, so
it'll be 3 halves to the -1. I don't know what the correct answer here is. I haven't checked this, but it should
yeah,
come out to be.
So I guess so. I think the problem is like the negative 2 and the negative 2 will cancel here. So because we have, let me just
Oh, you're right. I see.
So it was basically still turn out the
Yeah.
same. All right. How about
I can double check this. I'll see where the.
okay. I mean, I think it's worth looking at a little bit closer. Let's. I think it probably also had to do with the absolute value. I left out right here. Let me try this again one more time. Being a little bit more careful. Again, this is so I kind of do this on purpose. Don't actually try them out beforehand because I want you guys to see the process. And it's not always straightforward the right away. So let's think about it for this right here. So let's assume that K is positive, and so we have our the rate of change of our temperature with respect to time is going to be proportional to T naught minus T. Let's just quick double check that that's how the book works it. Okay. So again, we can do separation of variables. So we have 1 over T naught minus T equals K T time. And we're going.
It does say that the change in temperature should be K times T minus Tm, where M is the Tm is the median temperature.
Yeah, I just saw that. And so that would basically, you can do that as long as K is negative.
Yeah, exactly.
So interesting. So let me try this a little bit more time, one more time, and we'll try and make sure that we think about what we're doing each time. So we have T naught minus T natural log. So normally you would have an absolute value in here. So that means that we want this to be positive inside here. Assume that this is positive. And that is true in this case, right? Because the oven temperature is higher than the thermometer temperature. So this is positive, so we don't need to worry about absolute values right now. All right, so I think that's good. This will be KTC. And again, we do base E, so we get E to the K T plus C, or C E to the K T is T naught minus T. Okay, rearranging those things, we get an expression, add that across, so we get the temperature of the thermometer should be T naught minus C E to the K T. All right. And then we have our three equations here. So we know that at the beginning, at K equals 0, T is 70. Okay, so we know that 70 equals the oven temperature minus C. Okay. And then we know that after half a minute, it's 100 degrees. So that's going to be T naught minus C E to the K over half. And we know after 1 minute, it's going to be 145. 145 T naught minus C e to the K. All right. So again, our goal is to solve for T0. Again, it's kind of a little tricky here. We kind of need to get rid of the T naught at first.
T naught
So
is a constant, right?
that's correct.
And T is the variable. So the natural log should have a negative out front after you integrate because the derivative.
Here.
Yeah.
Oh, okay, yeah, there we go. Let's see here. Yep. So
That hopefully
there it
is
is.
all that's happened. I think
Yep.
that might be all that's happened because I couldn't spot another real issue.
Okay, that is true, yeah, because so again, I forgot to do some chain rule right here. So that the negative sign in front of the capital T, basically that'll put a negative over here. Well, so that when we get a negative K minus C. And again, when you bring that down, it's just going to be some other constant. We have a negative K here. All right, so we got a negative K, negative K, negative K. All right. So I want to kind of subtract these from one another so I can get rid of the T naughts and get just in terms of the C's and K's. So if I do 100 minus 70, that gives me 30. T naught minus T naught will cancel. We'll have negative C e to the negative K halves minus negative C plus C. So we factor out the C, we get, this is C 1 minus e to the negative K over T2. All right, equals 30. If I do the same thing with these last two equations, 145 minus 100 is 45. T0 minus T0 is cancels. We're left with negative C e to the negative K minus negative, so plus C e to the negative K over 2. All right, again, we want to factor out a C, but then we can also factor out an e to the negative K over 2. All right. So we're left with, this is just 1 right here, minus this is e to the negative K over 2. Right, because e to the negative K over 2 times e to the negative K over 2, we add the exponents, that'll add up to negative K. Okay, I think that's good so far. Now, if we divide these two equations, we can cancel out the C's and solve for K. So if we do that, we get 45 divided by 30 is, factor out the 15 is 3 halves. C over C cancels. 1 minus e to the negative K over 2. 1 minus e to the negative K over 2. That cancels. And so we just have e to the negative K over 2 left. Good so far? All right, so now
I believe so.
this is gonna, I think we're gonna run into the same thing here again. So let's just keep going. So natural log, both sides, e to the negative K over 2. Natural log of 3 halves. We're left with negative K over 2, natural log of 3 halves. And again, we can multiply that then negative 2 across, we get negative 2 natural log of 3 halves plus k. All right. So plugging that k, that value of k, into one of these equations up here, let's just pick one. So we get 30 equals c 1 minus e to the negative so negative, and then k we have is negative 2 natural log 3 halves divided by 2. So the negatives and 2's cancel out. We're just left with 1 minus 3 halves equals 30. All right, that looks very similar, but I think we're good. I think we have a sign difference here. So we have c 1 minus 3 halves, that's negative a half. Multiply that across. That means c is going to be negative 60. Okay, that's good. So now when we plug it back into this first equation up here, we have 70 equals the oven temperature. Oh my goodness. Sign here again. So plus negative minus 60. Well, interesting. I will have to work this through and get back to you guys with the solution to this problem. I think I'm just making a sign error here somewhere. So anyways, let's move on. But so the key parts of this problem still are this Newton's law of heating and cooling. So I guess I want to just iterate that. When we're dealing with two things that are changing in temperature, we're dealing with differential equations of this form, where the rate of change of the temperature is proportional to the difference in the temperature. Okay. So that's what to be aware of. And then they also kind of this key here of when you're solving these equations, you have to try and divide to cancel out the c's, and that can get a little tricky. So let me work through there. I'm guessing what I'm running into is something to do with this antiderivative natural log here and the sign error. So I will post a full solution to that sometime. All right. All right, so let's take a look at this last example here in the last few minutes. So another example that in this section is when dealing with these tanks of liquid. Okay, so you can think of, we have a big tank of liquid. In this example, it's filled with 100 gallons of liquid, and there's 10 pounds of salt in the liquid. Okay, we're pumping a mixture into the tank, and we're pumping a mixture out of the tank. Okay, the key to these problems is that what's coming out is the well mixed version of the fluid. So let me just read this here. So a large tank is filled with 100 gallons of fluid, which 10 pounds of salt is involved. Brine containing half a pound of salt per gallon is pumped into the tank at a rate of 6 gallons per minute. Then is mixed up. The well mixed solution is pumped out at a slow rate of 4 gallons per minute. And we want to know what is the number of pounds of salt in the tank after 30 minutes. So again, we want to just set up a differential equation. So it helps to label things. So for example, I might say S of T is the number of pounds of salt in the tank after T minutes. Okay. And then we know a couple things. So we know that initially there's 10 pounds. So S of 0 is 10. All right. And then as far as the differential equation goes, basically the change in the number of pounds of salt with respect to time is going to be the rate in minus the rate out. Okay, that's in all these problems, that's what basically comes down to. The change in the amount of salt is basically the amount of salt in per time minus the rate of the salt out per time. Okay, so what's the rate in? The rate in, it says, is a half a pound of salt. Okay, so the rate in per gallon at a rate of 6 gallons per minute. So what would that be? So we have 1/2 of a pound per gallon times 6 gallons per minute. So that would be 3 pounds per minute. Okay, that's good. We want to just double check our units. This should be the same unit as DSDT, and that's the units of DSDT is going to be in pounds of salt per minute. Okay, so we're good. The units check out there. Okay, so this rate in is just a constant 3 pounds per minute. What's the rate out going to be? So the rate out is it's the well mixed solution pumped out. So this is the well mixed solution pumped out at 4 gallons. So we know that this is pumped out at 4 gallons per minute. All right, and then the rate out is the well mixed solution is the amount of salt in there per, right? It's going to be the amount of pounds of salt in the whole tank divided by the amount of water in the whole tank. Okay, so what would that be? So generally, if we assume that there's always 100 gallons of fluid in the tank, it would be S, the number of pounds divided by 100. Right. So if there was at the beginning, there's 10 pounds of salt and 100 gallons. The initial mixture is 1/10 pounds of salt per gallon times the 4 gallons per minute out. However, this 100 is not staying the same because we see that it's coming in at 6 gallons a minute and it's going out at 4 gallons a minute. So this amount of liquid actually is not 100. It's going to be 100 plus 2T, right? Because there's 2 gallons per minute increase in the amount of liquid in the tank. Okay, so that makes it a little bit more complicated. All right, so the rate out here is this S over 100 plus 2T times 4. And again, we're kind of just checking the units. This is in pounds per gallon, and the gallons will cancel out pounds per minute. So the units of this is, again, it's pounds per minute. Okay. All right, so our differential equation, ds dt, then is 3 minus 4 S over 100 plus 2T. All right, so we want to try and solve this equation here. And we want to, really, the question is asking us what is S after 30 minutes? Okay. So we found a formula for S of T, then we can solve for S of 30. So we need to solve this differential equation here. Okay, so the problems we've been doing so far have been separable. That is not going to be the case here. So we're just looking at this problem. We see we have a constant here. It doesn't have S or T in it. If there's no T, it's always separable because you can divide the whole thing across. However, in this case, there is a T, and so we can't just divide everything across the other side. So this is actually going to be, we're going to be a linear equation here. So let's rewrite it in that form. So we rewrite it as ds dt plus 4 over 100 plus 2t times s equals 3, right? So this problem here is first order linear, and it's non-homogeneous, so we can use an integrating factor to solve this one. So our integrating factor, recall, is mu is e to the antiderivative of p of t. In this case, p is this function here, 4 over 100 plus 2t. So it's going to be, so the antiderivative of p with respect to t is the antiderivative of 4 over 100 plus 2t. Okay, so doing that, we can pull the 4 out front. That's 1 over this 100 plus 2t. If we were to do like kind of a substitution, we would see we would get a natural log. So it'd be the natural log of 100 plus 2t. And then there's a 2 in here. So that means we need to divide by a 2 out front. So that's the antiderivative. It's 2 to the natural log 100 plus 2t. And again, we're going to do base e of that. So we base e to that thing, 2 natural log 100 plus 2t. Bring the 2 into the exponent, we get e to the natural log 100 plus 2t squared. Cancel that, we have 100 plus 2t squared. So that's our integrating factor mu, 100 plus 2t squared. All right, so now that we know mu, we know that our solution then is, just immediately going to that formula, is 1 over mu, the antiderivative of mu times our 3 right here, times our function on the right-hand side, times 3. Right, so that's 1 over 100 plus 2t squared, antiderivative of 3 times that. Okay, that formula comes from, right, from our section on linear differential equations. All right, so now we just need to do this antiderivative. So S, let's focus on that antiderivative. So the 3 can kind of come out. That's fine. So we just need to do the antiderivative of 100 plus 2t squared dt. Okay, so there's nothing to do a substitution with on here. So basically, you have to FOIL this out and do the power rule. This is the antiderivative of 100 squared plus 2 times 100, so 400 t plus 4t squared dt. Do the antiderivative, we have 100 squared t plus 200 t squared plus 4/3 t cubed plus a constant. Okay, so that's that. And then we can plug that into our formula here. So we have 3 over 100 plus 2t squared times this whole thing here. So 3 4/3 t cubed plus 200 t squared plus 100 squared t plus a constant. All right, the constant we need to find, we can use that as our initial condition. So our initial condition in this case is s of 0 is 10. So if we plug in s of 0, we get 3 over 100 squared. All those go away. times C equals 10. So then C has to equal 10 times 100 squared 3. Plug that in, and then the S of a 30 is just plugging into this formula right here. Okay. So I won't do that right now, but you could do that if you wanted to. So you just plug in 30 to that formula with this value of C. Okay. So those are those examples. I will post a solution to that second example explaining how to do that type of problem and what went wrong with that example. But if you're watching this, go ahead and get your own and see if you can do that example. All right.